Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of Pfizer Berhampur. So I am the TA of this course Retrosynthesis in Organic Chemistry, instructed by Professor Shamik Nanda from IIT Kharagpur. So in these classes, I usually discuss about some important reaction mechanisms and name reactions to approach retrosynthesis of any organic molecule. So to plan a retrosynthesis of an organic molecule, you have to know some small reactions. Unless you can't approach or design retrosynthesis of any compound. So actually the retrosynthesis is a combination, a gathering of multiple small name reactions and also normal transformation reactions. So here in the previous classes I have discussed about some important name reactions which have been again and again mentioned in your assignments. Moreover, I have also discussed about some reaction mechanisms and their stereochemical aspects, like how from the substrate you can predict the stereochemistry of the product, or from the product how can you predict the stereochemistry of the substrate. So if you have given any compound, so in that case it will be if you know the stereochemical aspects of any compound, it will be easier for you to design the retrosynthesis of that compound. So let's start. So in this class I will discuss about, in the previous class I also discussed about the stereochemical aspect for forming a double bond. We have discussed about E2 reaction, which is usually a trans elimination. There is another type of elimination which is called scene elimination. So we will discuss about that and how we can apply that type of elimination in some product formation. We will also pursue that, and we will also solve some miscellaneous previous year questions. So another type of elimination is EI elimination, means elimination intramolecular or intermolecular. When in this case there is a thermal scene elimination. EI elimination is a scene elimination. It is the same type of in case of E2 elimination as the beta hydrogen is eliminated. In this case also the beta hydrogen is eliminated, but here the requirement is that there will be a scene elimination, that the eliminating group and the hydrogen should be seen to each other. See, in this case, how is this possible? In this scene manner, this H oxygen will take up this H and this comes here and is eliminated. This is how we can get our product. So what are the main point of this elimination? It is a special type of elimination reaction in which two vicinal substituent on an alkene framework leave simultaneously via a cyclic transition state to form an alkene in cell elimination manner. In this case, we do not require any additional reagent. And this reaction is often found in pyrolysis. So this reaction can pursue in different type of mechanism. First one is the 6-member transition state. Reaction can go through a 6-member transition state. Reaction can also go through a 5-member transition state and also a 4-member transition state. The elimination must be seen. An atom should be coplanar for 4 and 5-member transition state, but the coplanarity is not required in case of 6-member, but it will if the hydrogen should be cis to the eliminating bond. So here one example is given. So you have to find the adjacent beta hydrogen. There is a hydrogen. So this O minus will take up this proton. Sorry, this is not beta. This is alpha. This is beta. There is a hydrogen. This O minus will take up this hydrogen and sulfoxide get neutralized. Okay, this is another one. So here I have already mentioned the product. So you have to predict the mechanism. What will be the mechanism? How will you get this product from this substrate? What will be the mechanism? So in this case, we know ED3N is a base and ketone can, the alpha hydrogen adjacent to the ketone is acidic. So this will be eliminated, generating a negative charge. Then when we add selenium chloride, this O minus attack to the selenium and chlorine in the system. Then if we done oxidation, seleniums are prone to oxidize. Now there is H available. So to take up this proton, get our desired product. Okay. This is another. What will be the product for this one? Before that, let's solve this one. These two are easier. So here, so if there is a nitrogenous compound and MCPP is given, nitrogenous compound can be oxidized. This type of reaction is called Chugge cope elimination. This type of elimination is called, when there is a nitrogen is involved, that elimination is called cope elimination. Nitrogen involved C eliminations are called cope elimination. It's called cope elimination. Now there are two beta positions. Cope elimination for here eliminated. Why this proton? Because see, this proton is anti to each other, but this proton is seen to this nitrogen. I have already told, in case of EI elimination, the eliminating bond and the eliminating hydrogen should be seen to each other. So this hydrogen won't be eliminated. It will be selectively take up this proton and eliminated to give a double bond at this place. The product will be next is this one. In similar way, this iodine will be oxidized. There is no H, but the CH3 has a H. It will take up this H. Okay. Now in this case you can ask why the iodine is getting oxidized, not the sulfur, because MCPB also can oxidize sulfur. Here sulfur is at its highest oxidation state, is already doubly oxidized. So there is no chance the sulfur to get oxidized more. So that's why the iodine will get oxidized. Let's try to solve this one. In this case, what will happen? First, this PPC has a better nucleophilicity, so it will eliminate, forming after that what will happen? This alcohol will attract to this phosphorus because oxygen phosphorus bond are the strongest bond. Selenium minus will be generated. Now if you just keep the stereochemistry of the substrate, then it will be easier for you to what is the change is happening. Suppose this is above the pen. So till now, as O minus is involved, so still now it will be above the pen. Now to this oxygen center, selenium will enter and it will be eliminated. Now selenium, as the oxygen was above the plane, the selenium has entered below the plane. pH, I am just drawing it in short form, PHNO2. Now what will happen? Now what will happen? In presence of oxidizing agent, the selenium will be oxidized, and after oxidation the selenium will be oxidized, and after oxidation it will eliminate this H, generating this as our product. Okay, this is how we can eliminate the oxygen and enter the selenium. Okay, let's go to the next type of scene elimination, that is Chugev elimination. So the Chugev elimination is a chemical reaction that involves the elimination of water from alcohols to produce an alkene. The intermediate is a xanthate. So if you have an alcohol and you add carbon disulfide, and NaOH, what will happen? This NaOH will take up this proton, then O minus this NH will take up the proton, then O minus will attack to this carbon sulfide, forming this thioester. After that, S minus will attack to this CH3I and we will get this thioester compound. Now under 400 degree above greater than equal to 400 degree centigrade, this xanthate ester undergoes a pyrolysis through syn elimination, where it is selectively eliminate the syn hydrogen and give us this as our product. In this case, as a side product, we get this and a thianol. Now here two stereoisomers are given. Two stereoisomers are given. One is erythro, another is strio, and treated in under same reaction condition. What will be the product? So here you can see from the stereochemistry of the substrate, from a specific stereochemistry of the substrate, you will get a specific stereochemistry of the product. So this type of reaction are stereospecific because the reaction intermediate are always prone to syn hydrogen. Therefore, a specific stereochemistry of the substrate will lead to a specific stereochemistry of the product. So here, let's start what will happen. In this case, in presence of potassium, this OH will be eliminated. Minus similarly in this case also in the both case the H is seen with this oxygen atom. So after CH2 and methyl iodide, it will form. I am just drawing the reacting part, okay, for simplicity. After CH2, like in the previous reaction, I have already told. So it will be first oxygen will attack to CH2, then the S minus will attack to the methyl iodide, forming thioester. So this under heating, this will come here, eliminated. So it will give us a E double bond. It will give us a E double bond or E alkene. Whereas in this case, in a similar manner, we will get Z double bond, Z alkene. Okay. So from a specific stereochemistry of the substrate, from erythro we will always get E through this through elimination, and whereas from trio we will always get Z. There is another type of elimination that is called Peterson elimination. It can be performed in both the way, like seal elimination and anti-elimination. Just vary the nature of the reagent, we can change the mechanism of the reaction. So Peterson reaction is stereospecific. In principle, it can therefore be used to make single geometrical isomer of alkene, and the geometrical depending on the relative stereochemistry of the starting material. Now if the reaction is acid catalyzed, E2 elimination will take place. What will happen in this case? If it is acid catalyzed, OH will be acidified to transform into a good leaving group OH2 plus. Then through a E2 elimination type, like this one will come here and it will get removed. In this way it will always give, so it will undergo the E2 elimination. But in this case, when the reaction is base catalyzed, the reaction will go through a syn elimination. What happens in this case? First, in presence of base, the OH will take up the proton, it will generate O minus. After that, this O minus will form a cyclic intermediate with this silicon, and through ring cleavage it will give us our desired product. So to get this cyclic transition state, O minus should be syn to this silicon, so it will undergo the syn elimination. Okay, so just by varying the nature of the catalyst, you can determine the stereochemistry of the product. So if the reaction is acid catalyzed, the reaction will go through a anti-elimination, and if the reaction is base catalyzed, the reaction will go through a syn elimination. Here one question was given in GATE 2023. The stereoisomer of the G giving the depicted product is, so what will be the stereoisomer? To get this specific product, what should be the stereochemistry of the substrate? So let's try to perform the reaction for each of the substrate, and let's see for which one. So it can be multiple answer can be there. So first we have to see, so silicon is given, so this is Peterson elimination. Whenever the silicon is given, silicon and OH, that means it's a Peterson elimination. Now we have to see how this reaction has been catalyzed. The reaction has been catalyzed through acid or base. So BF3OH2 is a Lewis acid. Due to that, this is acid catalyzed, so reaction will go through a anti-elimination. Reaction will go through a anti-elimination. Reaction will go through anti-elimination. So let's start here. Both the OH and silicon are in the same plane, so it will not go through a anti-elimination. So this is cut. Here the OH and silicon are in the opposite plane, so it will go through a anti-elimination. So what will be the product? From the stereochemistry of the substrate you can see, from the product you can see there is a Z double bond, but here the double bond is E in nature, so this is not possible also. Here this is also opposite plane, but it will lead to a E double bond. So the only possibility is if we turn the double bond. If we just turn the double bond. So in this case there will be a rotation across the single bond. So this is not also possible. So in this case what will happen, there will be a rotation along the single bond. So OH comes here, ethyl goes here, C4H9 comes here. See, in this case the silicon and the OH are opposite to each other, undergoes elimination. Undergoes elimination. So this will be our product. Similarly, in this case also, it will undergoes a bond rotation. For that, ethyl goes here, OH goes here. In this case also, now it can undergo, because the silicon and OH are at the opposite plane. So it will undergoes elimination to give us our desired product. Okay, let's go to our next question. This is also silicon is given, so it will be Peterson olefination. Next, KH is given, so this is a base. So in presence of base, what elimination will goes? It will undergo the seen elimination. So among these two OH, which one is the seen one? This one is the seen. So the elimination will be from this side. Only the seen, it will be seen elimination. So therefore it will be specific towards this OH, leading to a double bond at this place. Now in presence of MCPPA, double bond will be, epoxidation will be take place. So which one will be our product? So now here is another stereochemical aspect for a reaction of double bond. In the last class I have told that for epoxidation reagent, that per acid we are using, that can form a hydrogen bond with the adjacent OH. Now the adjacent OH is below the plane, so epoxidation will take place from the below the plane. So if the epoxidation is taking place from the below the plane, there are two H available here. If the epoxidation is taking place from the below the plane, these two H will go above the plane. So these two OH go above the plane. So the correct option will be option B. Understood? Because the coordinating OH group is below the plane, so the MCPP will come, epoxidation will take place from the below the plane, and as the epoxide is forming below the plane, so the rest 2H atom will go above the plane, giving us this as our product. Okay. The major stereoisomer P obtained in the following reaction. So I am giving this as a homework. Just give it a shot. I will solve this in the next class. Next class we will discuss about some retrosynthesis of some compound. I will try to gather some important molecule and we will try to design their retrosynthesis of those compounds. So this is one of the homework. You can try. We will discuss it in the next class. So what will be the reaction? In the following reaction? Understood, na? Everyone please note down the major stereoisomer formed in the following reaction. In the following reaction, what will be the major product X? So we know that in amine, if you add acid, what happens? This will get diazotized. This is one type of semi-pinacol-pinacolone type of reaction. We know that what happens in pinacol-pinacolone, the adjacent group will be eliminated, then there will be a shifting from the adjacent carbon. So this is N2 plus will be generated. Now it will be eliminated, generating a positive charge. This is semi-pinacol-pinacolone rearrangement. Semi-pinacol-pinacolone rearrangement. It will be OH. Now there is a H available. So there is H will be shifted to this position. Now positive charge is shifted from this carbon to this carbon. So it undergoes neutralization, giving us this as our product. So this is an example of semi-pinacol-pinacolone rearrangement. So don't get confused why NH2 is given or something. So you have to know that this will be as same as pinacol-pinacolone rearrangement. So what will happen in this case? We know whenever Br2 is given to a double bond, there is a anti-addition. always Br2 is added in an anti manner, because this going through a bromonium carbocation intermediate, bromonium intermediate. This will undergo a bromonium intermediate. So the product will be a dibrominated compound, but both the bromine will be anti to each other. Now they have added amine, but in excess. So as excess is mentioned, so both the bromine will be eliminated. Now, as we know that in case of SN2 elimination, what happens? There is an inversion of configuration. So this bromine, once it is attacked by a amine, this center will be inverted. Similarly, once it attacked by a amine, this center will be also inverted. So in this case, if suppose this was above the plane, this was below the plane. So after reaction, this will be below the plane and this will be above the plane. The correct option will be option C. Okay, so there is actually in the both the reacting side there is a SN2 elimination. So both the center will be inverted. What will be the major product formed in the following photochemical reaction? So first, what will happen in this case? So as we know, THCl is given, so as OH is also given. So first thing comes in everyone's mind that it will form OTS. It will form OTS. What will happen now? After that, now this bond is anti to this bond. So it comes here and OTS is eliminated. Just if we draw this structure in a different way, so there is also 2 carbon, there is also 2 carbon, so I am drawing in a symmetrical way. So the carbon center is shifted to this position. Now the eliminated OTS can again attack to this position, giving us this as our. So now the attack can be both from, as it is a carbocation, the attack can be from both the side, above the plane and below the plane. But as the above the plane, the exoside is blocked by this big bulky group, so the attack will be from the below the plane, giving B as our product. Okay. So this is also stereochemical aspect, that if the exoside is blocked, if not, the exo attack is always favorable, but if the exoside is blocked, the attack will be from the concave side, giving us OTS as our product. what will be the major product in the following reaction? In the last class we have discussed about hydroboration reaction, how this reaction take place. This reaction take place following anti-Markovnikov rule. You know about that, it will always follow a anti-Markovnikov rule. What is anti-Markovnikov rule? That the hydrogen will be added where the hydrogen, according to Markovnikov rule, the hydrogen will be added where at the less hindered side. But in case of anti-Markovnikov rule, the hydrogen will be added to the more hindered side. So the product will be boron will be added to the less hindered side, whereas hydrogen will be added to the more hindered side. Now this addition will be seen. So if the product C, all the methyl are above the plane, so the H will be below the plane, and because of that this boron will be also below the plane, because there will be seen addition. There will be a seen addition. Now the next step, if we add hydrogen peroxide and NaOH, what will happen? This carbon-boron bond will be substituted with the carbon-oxygen bond, and in that case the oxygen will be below the plane. So the correct option will be option B. Correct option is just this boron bond, carbon-boron bond will be eliminated, substituted with the carbon-oxygen bond. The stereochemistry will be retained. Okay. So let's try to solve some multiple steps question which will help you to get an idea how to predict the retrosynthesis of any compound. So you have to plan the retrosynthesis of this compound from this one. How will you get this compound? We have to plan the retrosynthesis to get this compound from this substrate. So here everything is written, just the OH has been eliminated. The first option is given that, so just try to solve according to one by one. So in the first one, what will happen? This will be a ester, thioester, and there is a below H. It will be eliminated and create a double bond here. And through BU3SNH, this double bond can be reduced. Next is I2PPH3 imidazole. It will also create a double bond here, but here they have added H2PD. So its H2PD can reduce this double bond also. This H2PD can reduce this double bond also. Because of that, so let's start. First, just for A, there will be a 6 member. Now this reagent we have discussed earlier also. This is a reagent of Chugav reaction. So what will happen? It will form a thioester. Will form a thioester. Now we know there is a CH is available. But you have to notice that it will form up to this. But you have to notice in the second step, I have told already, in case of Chugav reaction, you have to heat the substrate at a very high temperature, like greater than equal to 400 degrees centigrade. So in the second step, they have not mentioned about the heat. So it will not undergo Chugav type of reaction. Whereas before it can go to a Chugav type of reaction, the next reaction will take place in the reaction. So that is SN. This is it. So we know that Bu3SNH and AIBA generate Bu3SN dot Bu3SN dot. See this SN dot SN dot will add up to this sulfur. This goes here and this one breaks. See, I have shown in a single headed arrow because the dot is reacting, a radical is reacting, so you have to show through a single headed arrow. I am not writing the OBN. Okay. So there will be a radical generator. Now this radical will take proton from Bu3SN, another molecule of Bu3SNH. We get our desired product. Let's try the another. So in the first one that we were getting the product, let's try the second. We forget just to be sure. So why not B? See there, by seeing the second reagent you can eliminate that they have added H2PD. So we know that H2PD are prone to reduce the double bond, which is less electron rich. So between these two, if there is a double bond here, now as there is a double bond already in this place, so it is prone to reduce this double bond also. But here in the subproduct, the double bond was intact. So B will be not our desired process. In this one, so this OH will be silicon So the correct option will be option A. Let's go to the next question. What will be the major product formed in the following reaction sequence? So what will be the major product formed? In the following reaction sequence. So first, this reaction we have discussed earlier also. This is Eastern-Moser fragmentation reaction. We have discussed in one of the classes this, because this name reaction has been mentioned in your assignments multiple times. So we have discussed about this name reaction earlier also. So what will happen? In presence of H2O2, this double bond will be epoxide. The next step, tosyl hydrogen is given. So now, if you add tertiary butoxide, what will happen? In presence of tertiary butoxide or base, it will take the proton from this place. It will take a proton from this nitrogen center. Now, this will come here. Opens up this epoxide. There is a double bond and a double bond between nitrogen and nitrogen. Now this O minus will be neutralized and break this carbon-carbon bond, and there will be elimination of N2 molecule. Giving our alkyne here and a ketone here. Now if you treated this with H2PD, calcium carbonate and quinoline, it will undergo a partial reduction and this double bond will be partially reduced. This triple bond will be partially reduced to give this as our product, because the triple bond will be partially, this triple bond will be partially reduced to give this as our product. Okay. Understood? Let's go to the next one. So we have discussed about this type of reaction. If selenium is given and if you are adding oxidizing reagent, what will happen? We have discussed about this type of reaction. So what will happen? It will undergo the oxidation. Undergoes oxidation. Now we know the chemical reactivity of hydrogen and deuterium is almost same. So now which one will be eliminated? Hydrogen or deuterium? Obviously hydrogen, because this type of elimination always undergoes through a syn elimination. So whichever is syn to this selenium, that will be eliminated. So hydrogen is syn, so hydrogen will be eliminated from the system, giving a trans alkene with deuterium, a deuterated trans alkene. Okay, so this type of strategy we can use in our reactions also to get an idea about the mechanism. Deuterium leveling experiment, we can do this in any unknown reactions also. So understood? Because the hydrogen is syn to the selenium, so it will be selectively eliminated, not the deuterium. The most suitable reagent combination of A and C. A to C, sorry, A and C. A to C. So what will be the? So in case of here, once substrate is given. Now in case of A, this alpha beta unsaturated double bond is getting reduced, not this one. So this is only possible for Barch reduction. This is only possible for Barch reduction. So A will be obviously between Barch reduction. So the option will be between A or B. These two are already cut, because alpha beta unsaturated double bond can be reduced by Barch reduction only. Okay. Next, B. In case of B, this alpha beta unsaturated ketone is getting reduced. So that is possible by Luce reduction. So both the B are Luce reduction. So still the options can be between A and B. The last option will be determined. So here this double bond is getting reduced. So they have given, in the one case they have given this Wilkinson catalyst, and in the second one they have given hydrogen palladium. So as this is just a double bond reduction, so the reaction will go through a option B, H2PD, hydrogen palladium sulfur, because Wilkinson catalyst act as a hydrogen, it will not reduce this double bond. So the correct option will be option D. Okay. This is also a homework. Try to get an idea the retrosynthesis of this compound. We'll solve it together in the next class. So I have already given one homework earlier, and this is another one. We will discuss this in the next class. Just take a look. We will discuss this in the next class. So what will be the major product formed in the following reaction sequence? Just let's go step by step. By solving this type of question, you will get an idea how to plan a retrosynthesis of any compound. So let's go step by step. So first they have given ethyl acyl chloride, what will happen? So if we given this OH will be acylated. This OH will be acylated. Next, they have given LDA. So in presence of LDA, what will happen? There is a alpha hydrogen available here. So in presence of LDA and TMSCl, so this proton will be eliminated through a enol formation. Then oxygen will attack to this TMS. Forming OTMS. Now in presence of heat, this will undergo the Claisen rearrangement 3,3 sigmatopic reaction. As this group is above the plane and it is a concerted process, so this will come also above the plane. So this is concerted process, and as it is detaching from the above the plane, it will enter here from the above the plane. Next, they have given H plus. In presence of H plus, this ester will be acidified or hydrolyzed, forming OH. I'm just drawing this part. The rest part will be same. Now in presence of nitromethane, there will be a methyl esterification, it will be OMe. So the correct option will be option D. Understood? This will be CO2Me. This will be CO2Me by using CH2N2, and we will get this as our product. What will be the major product formed in the following reaction sequence? So they are given zinc. So zinc has a very prone. So in case of Swarovski reaction, the zinc get incorporated between this CBr bond. For shortcut you can remember like this, but mechanism is not like that. Mechanism, first zinc will attack to the oxygen, this bond will go here, and so I am not discussing about the mechanism. For shortcut you can remember in that way, that if to a alpha bromo ester, if zinc is given, zinc will be incorporated between the carbon halogen bond. So it will be a zinc Br. So it will act as a Grignard type of reagent. So that will, there is a delta negative charge. As it is a metal, it will be delta positive. So the delta negative charge will attack to this so in presence of negative charge. So now there is acid is given. Now in medium acid is given. So as this is delta negative charge, it will be protonated. Forming this now in presence of phenyl selenium anion, what will happen? It will eliminate this bromine atom, because it is a only electrophilic center here. It can't attack to the ester center, so this center is more electrophilic, so that will attack to this electrophilic center and bromine will be eliminated. Further, when we add MCPPA, this selenium will get oxidized. Forming this as our product. Selenium will be oxidized. Now, as there is a, we know in case of UI elimination, as there is a H available, it will take up this H and undergoes a scene elimination. So the correct option will be option A. Okay, understood? So this is the last question of today's session. What is the correct combination of reagent to affect the following conversation? So you have to plan the synthesis of this product from this substrate, You have to plan the retrosynthesis or the synthesis of this product from this substrate. So let's start. So I haven't discussed about this name reaction. In the next class I will discuss. Whenever you add in a ketone, you add docile hydrogen and a strong base like butyl lithium, two equivalent of strong base like butyl lithium. What happens? I haven't discussed about this name reaction yet. I'll try to discuss it in the next class. In a ketone, cyclic ketone, if you add a docile hydrogen and two equivalent of strong base like butyl lithium, you have to add strong base. What happens? In that case, there will be a formation of double bond and a negative charge here. This is to remember this as a shortcut. There will be a double bond from the alpha position and there will be a negative charge where the carbonyl position were. Now, if you add now, you can see. So from there you can understand that whenever there is a docile hydrogen and a strong base like butyl lithium, there will be a double bond formation and there will be a negative charge where the carbonyl position. This is a shortcut to remember. I will discuss about this namely. I know the mechanism, but I can't recall the name. I will discuss about this in the next class. Then you can see from the product that there is an incorporation of acid group. There is an incorporation of acid group. Now, from the synthon and knowledge, you know that whenever you need a aldehyde, whenever you need a CHO group, the source of a CHO group will usually be the DMF, because DMF leads to, this is the NME2 dimethyl formamide. So whenever you need, it acts as a good leaving group, NME2. So whenever you need a aldehyde, you can use DMF, so that this part removes and you can get CHO as our substituent. But whenever you need a carboxylic acid, the perfect synthon for that is carbon dioxide. So if you add carbon dioxide to this, what will happen? This negative charge will attack to this carbon center and this open up, give CO2 minus, CO2 minus. Now if we add, now it can take a proton, because already there is any docile hydrogen in the medium. You can take a proton and we can get our desired product. So what will be the correct option? Option C. So whenever you can see that there is an incorporation of carboxylic group, you can get an idea that we have to use carbon dioxide as one of our synthetic equivalent. And if you see there is a aldehyde group, then you can use EMF as our synthetic equivalent. So this much for today's class. Thank you everyone. So for this today's I have given 2 homework, this one and this one. So just give it a shot. I will upload the video and the slides. So just try by yourself to get the answer. Options are given. So and we will solve this in the next class at the same time next Sunday. Okay. So this was overview of today's class. I hope you have understood. So thank you everyone. Have a nice day.